Okay, so the first problem we're going to work is page 70, number 22. A car starts from rest and travels for 5 seconds with a uniform acceleration of 1.5 meters per second square. So as soon as you see that, the velocity and the acceleration have the same sign. What does that mean? The velocity and acceleration have the same sign. It's speeding up, right? Car is speeding up in the first part of the problem. The driver then applies the brakes, causing a uniform acceleration of -2 meters per second square. So it starts to slow down there. If the brakes are applied for 3 seconds, how fast is the car going at the end of the braking period, and how far has it gone from its start? So I'm going to go over to another slide so I have some room. And we'll write down, first of all, what we know. We know the car started off VI 0. We know that it accelerated positive direction of 1.5 meters per second, and it did that for 5 seconds. So it's speeding up there to begin with. After that, we know that it hit the brakes. So we'll put a line here. We'll do the brake part in a different color. After it hit the brakes, its acceleration was -2. And it held the brakes in for 3 seconds. So I guess what we need to do first is work this problem in 2 parts. We'll work the first part of the problem in red and the second part in black. What's something that we need to know to make this problem work for us? It's probably the first thing we need to know. How fast was the car going at the end of the speeding up process, right? And we can find that using VF equals VI plus AT. So we know that VI is 0. We know that acceleration is 1.5. And we know that it's accelerating at that rate for 5 seconds. So if we do the math on that, we see that that's going to be, and this is supposed to be squared right here. We see that's going to be 7.5, right? So I'm going to go ahead and write down right here, VF equals 7.5 meters per second. That's as fast as that car ever gets, right? From here on out, it's going to be slowing down. What else do we probably need to know about the first part of the problem? How far does it go? So find a displacement. Let's do that. Several ways we could do it, but knowing what we know now, what's probably the easiest way to go about doing that? Probably the third equation down, which is delta x equals 1/2 VF plus VI times t. Probably the easiest way to go about it from what we know. So let's go delta x equals 1/2 7.5 plus 0 times 5 seconds. Now pay attention to your units on this. The seconds are going to cancel out, so we're left with meters. So if we do the math on this, 7.5 times 5 times 1/2. 18.8. And I'm going to go ahead and write that right up here. So delta x equals 18.8. All right, now that's all during the first part of the problem, when the car is still speeding up. Everybody okay with that? Then he starts to slow down. Not sure why this eraser is not completely cooperating today. Slowly it's working. We've got to scrub it a little bit. So now let's work the slowing down part of the problem. What else do we know now that we didn't write down to begin with for the black part of this problem, the slowing down part? We know the initial velocity, right? Down here now, the initial velocity is whatever the maximum velocity was in the top of the problem. 7.5. So what we need to figure out first is what? The final velocity. And again, we can go back to this equation up here that we were using before. Vf equals Vi plus AT. So Vf is going to equal 7.5 plus, we were accelerating at -2. And we did that for 3 seconds. Oops. Again, pay attention to your units. Seconds are going to cancel, leave behind meters per second. So over here, we're going to have -6 plus 7.5. We get Vf equals positive 1.5. Which means, at the end of this problem, the car is still going which way? Forward, but it's much slower. That's our first answer. So that's the answer to part A. The second part that we need to know, though, is the displacement. And again, we can use the same equation we used before. That works just fine. We started off, well, we ended with a final velocity of 1.5. We started at 7.5. And all that happened in 3 seconds. So if we do the math on there, in the middle we're going to have 9. So we've got 9 times 3 divided by 2. 13.5. But is that our answer? What was it asking for? The total displacement. First part of the problem we went 18.8. Second part of the problem we went 13.5. So add those up. 32.3. But this problem only needed how many significant digits? 2. So 32 meters. Positive 32 meters would be your answer on this one. Sound good? Any questions on that? Let's try a second one then. Let's try this one. This is a little more straightforward problem. A boy sledding down a hill accelerates at 1.4 meters per second squared. If he started from rest, in what distance would he reach a speed of 7 meters per second? So I'm going to write down over here on the board some stuff so I don't forget it. And then we'll put it on that smart board in a second. All right, so he starts off at VI is 0. He accelerates at 1.4. And we want to know at what distance does he reach a final velocity of 7 meters per second. All right, so let's go where we got some space to work. And think about a couple of things here. And again, I'm going to write down what I know. It's always good to do this. If he's sliding down a hill, why did I write positive 1.40 meters per second squared? He's going down the hill. Yeah, he's not going straight down the hill, right? He might be going down the hill to the what? To the right. So typically when you're talking about down the hill, you don't worry so much about the positives and negatives. You just make sure at the end of the problem you say down the hill or to the right or whatever. All right, so we also know the final velocity. And we're looking for the displacement. So if we look over at our equations to see which one would probably work the best for us, what do you guys think? I think probably the second one, right? You could go down and you could do the fourth one.
You found T and then.
Okay, yeah, it might actually be easier to do this one. You're right. VIT, we know both of those things. No, we don't. Plus 1/2 AT squared. And this one we can make it work. But to make that one work, what are we going to have to do? We're going to have to find the time, and to do that, we're going to have to do what? Quadratic equation. I prefer not to have to do that. So what else might be a good option? All right, the second one, but to use the second one, the second one will work fine, right? Yeah, that's probably the best option. So VF squared equals VI squared plus 2A delta X. We know VF and VI. We know acceleration. We don't know displacement. So that works. So let's do a little algebra and let's solve that out for delta X. We're going to subtract VI from both sides. And then we're going to divide both sides by 2A. Cancels out over here. So delta X equals VF squared minus VI squared over 2A. So if we plug in what we know, VF was 7, square that. So I'm going to go ahead and go with 49 meters square per second squared. 7 meters per second squared. Minus VI squared. Well, that was 0. All over 2 times our acceleration, which was 1.4. First of all, pay attention to your units. These are going to cancel with these and leave behind what? Meters. So essentially we've got 49 divided by 2.8. And so that's 17.5, and in this problem it looks like we need to keep 3 sig figs. So our answer, delta X equals 17.5 meters. That will be down the hill. Make sense? Anybody have questions on that? All right, we're going to go ahead and work one more of these. And that's the one about the rocket. This might have been the hardest one that you had on your homework. A rocket moves upward, starting from rest, with an acceleration of 29.4 meters per second squared. So again, I'm going to write down over here so I have my info. Starting from rest, we know the acceleration. We know the time that it accelerates, 3.98. And then it runs out of gas. So that means its engine's cut off. But it keeps going up, right? And as soon as its engine's cut off, what is its acceleration become? Negative 9.8. As soon as the engines go out. So it starts to slow down. And we want to know how high does it rise. So what else do we know? Its final velocity at its highest point has to be what? 0. So we're going to have to work this in 2 parts. Let's go to a place where we've got a little space. Oops. So let's put a blank slide up here so we've got some room. All right, so let's just work the engine's own part first. So I'm just going to say own. Engine's own. We're starting off with VI 0. Acceleration 29.4. Time 3.98. All right, from knowing that, just with the engine's own, what do we need to find? Final velocity, we probably ought to go ahead and find what? Displacement. Those are going to be easy to find, not a problem here. Let's go VF equals VI plus AT. So VF equals 0 plus 29.4 times 3.98. Cancel units. Multiply that out. We get 117 for our final velocity. I'm going to write that up here. Now that's as fast as it ever goes, right? It's top speed. We might as well go ahead and calculate the displacement. So the displacement, the easiest way to do that would probably be to use this equation. What you got? Thank you. Go ahead, Matt. So we got delta x equals 1/2, 117, the final velocity, plus 0, the initial velocity, times 3.98. All right, so let's do a little math on that. Let's go 117 times 3.98 divided by 2. And we end up with a displacement on that part of 233 meters. And actually, I'm going to keep a couple of extra significant digits, because what do we know we got to do with this eventually? Add it to the next part, right? So it's always good to carry out a couple of extra significant digits until the very end. So I'm going to go ahead and write down 232.83 meters. And we'll come back to that. All right, any questions on so far? All right, now let's continue, and this time let's look at the engines off part of the problem. For the engines off part, what's VI? 117, right? What's the final velocity for the engines off part? 0. And what's the acceleration for the engines off part? Negative 9.8. Now we were looking for in this problem time or just displacement? Just displacement? All right, so let's just find displacement. And from looking at this, probably the easiest way to find this displacement would be to use a couple ways we could do it, but probably this one would be the easiest way. Solve that out for delta x. So it would be VF squared minus VI squared over 2A equals delta x. Plug in what we know. So we got 117 squared minus 0 squared all over 2 times minus 9.8. Divide that out. 117 squared divided by 9.8. And we end up here with 1397. All right, now that's how far it goes up. That's how far it goes up after what? After the fuel runs out. It went up this far before the fuel ran out. Notice the difference. It didn't accelerate for very long, but it got up to a really fast speed. So it went a long way. So all we need to do is just add those together. 1397 plus 232.83. I think we need 3 sig figs on this problem. My answer says 1629.83. We need to round it to 3 sig figs, so 1630 meters. Yeah.
That's not what I got in the back
Maybe let's say 9. One's in.
Oh, I didn't multiply by 2. Let's fix that. Yep. So let's go 117 squared divided by 19.6, right? Yep. Yep. I messed up there, guys. Just fix that. So this comes up to be, just the second part of the problem, comes up to be 698. So then we need to take the 698 from the engine's off part plus the 232.83. And we end up with about 931. Is that more like it? Meters. All right. Any questions there? All right, let me stop this.